Hello everyone, July 22nd. Alright, let's do this. Surprise, it's not a hard one today. All possible full binary trees. Given an integer n, return a list of all possible full binary trees with n nodes. Each node of each tree is, and the answer must have node.value equals 0. That's fine. Each element of the answer is the root of one possible tree. You may return a full binary tree is a binary tree where each node has exactly 0 or 2 children. 0 or 2 children. And we need to return all of them. I guess the order doesn't matter. Okay, how do you think? Well, for each node, right, you can do, hold on, I haven't set up today's one yet. For each node, what you can do is you either produce no children, right, and have n equal to 7. That's the number of nodes. So we start from something, and then for that, on the left tree, right, what if n equal to 2? What if n equal to 2? What if n equal to 2? That's a good question. It's nothing because it's not possible. Yeah. So for each one, you either have 2 or you have nothing, right? So for this, I either have nothing. I mean, it depends, right? When you have a node and you know how many are left, right? If you have more than one left, then you need to, well, you have to see how many is left. If you have, because each one, if you do a node, right, then that one either have nothing. You don't keep going on, right? Or if you want to go on, you have to go 2. So you have to create a node here and create a node here. So I'm thinking backtracking, right? So we start from here and I say I want the left node and I want the right node. Yeah, it depends, right? It depends. If you have some node left, then you have to do a left and right. Okay? Then you go to a left, you go to a right. Then how many you go on the left and how many you go on the right? That's an interesting question. How many? I mean, it's always going to be, because each one has 2, right? So the bottom is always 3. So I think you either don't divide anymore. So you come here, right? You can decide whether you want to continue divide. So you can continue divide. If you decide not to divide, but you cannot not divide, right? You cannot not divide. So we can say, I'd say a dp, basically just dp remaining, right? We want to do that. dp remaining. How many remains? Okay? So we start from dpn, right? Then we say we want 2. Right, and we can say if n is equal to 1, right? N is 1, and we just return a node. If n is equal to 2, then we return a none, right? N equal to 2 is a none. And if n equal to 3, right, or n equal to 3, then you do 1, and you split it 2, right? And when you split the 2, you can split many different ways. You can split 1, remain minus 1. Two, remain minus 2. That's not possible. So 3, remain minus 3. Can we do 4? You cannot do 4. How do you do 4? You have 1. Right, now you have 3 left. You have 3 left. Right? You have to do this. You have to do this. Now you have 1 left. You cannot have 1 left. So I think n cannot be even number, right? 4 is not possible. N cannot be even number. No, it cannot be even number, right? N cannot be even number. So it's even simpler. So every one has to be odd. So we can say 1, 3, 5, all the way down. And because it's dp, right? So we have a value. So when we do 1, 3, I mean once we do 1, 3, we can do 3, 1 immediately, right? We can do 3, 1 immediately. Okay, so I think we have a strategy for this. Alrighty, we don't have to do this, but we need func tools. Where are you, cache? If n is equal to 1, return tree node. If n equal to 2, if n equal to 0, right? Return none. Otherwise we can say we have to return a list. Right? I have return a list as all the nodes, all the things that we can have. Okay, so now we can say for I in range 1, I think it's n divided by 2, then 2. We don't need to do half. Maybe we should do plus 1. But if n is odd, right? N is odd. So I say 5. 5 divided by 2 is 2. So we only do 1. So 1, 1, 4. You cannot do 1, 4. Oh, n minus 1. My bad. So it'll be 4, it'll be 2. So it'll be 1, 3. You know what? N minus equal 1, right? Now we do half. So we can have 1, 3. Then we cannot do 2, right? We cannot do 2. So yeah, so it'll be 1, 3, and 3, 1. Right? So on left will be 1. And in this case, it'll be 1, 5. 1, 5. And 1, 5, and then 3, 3. Right? So this will be 6. That will be 3. So I can do 1 and 2. Yeah, I think you should plus 1. Because we have to do 3. Right? Have to do 3. We have to do 3. Yeah, this will do 3. N is 6 divided by 2 is 3 plus 1 is 4. So I can do 1, 2, 3. So 1, we done it. 1, 5. 2 will skip. And the 3 will be 3, 3. And once we're done, we have 1 and 5, right? So 1 and 5, I have however many. Then we can set to 1 and however many. And then we can swap them, right? So basically this and this, we can swap. And then 3, 3. So we can say, how do we say it? Option 1 is equal to root 1, okay? Self dot this I root 2 equal to self dot. Well, if you do this first and then you do one more time, R3 equal to self dot this and divided by 2. Yeah, I see how it is. Rest equal to this, right? This is gonna be n minus I. Then what? Then we're gonna do for everything in this, we put in here, right? For everything in this, we put in there, and then we swap. So we can say for we can say root left. Oh, I shouldn't say root left. Root 1, root 2. So and then I can say for, come on, R1 in root 1, for R2 in root 2, root equal to tree node, okay? Then we say root dot left. Oh, hold a second. We do this, root dot left equal to R1. Rest dot append tree node left equal to R1. Right equal to R2. Then rest dot append tree node left equal to R2, right equal to R1. Once we're done, we got R3. Then we say rest dot append tree node left equal to R3, right equal to R3. Yeah, is that right? Yeah, n minus 1 divided by 2, that will be a 3. So we get this, so we have left and right. Then we'll return the rest. All right, let's take a look. Oh, well, we're gonna go with 1, 2, 3, 4, 5, 6, 7, 9, 10, 12, 13, 14, 15, 16, 17. Oh, forgot RU cache. $19, $20, $22, $24, $25. Oh, 20. I don't know why you think about 25. That's weird. Too fast, man. Too fast. I'm making these tiny mistakes. Unhashable type. Well, you don't need to hash. What do you mean unhashable type? Wait, hold a second. What do you mean by unhashable type? It's just a result. Wait a second. This is weird. Unhashable type. I don't need to hash the result. Hold on. This is interesting. We're not gonna do any result. I just want to see. All possible this and. Name optional is not defined. That's okay. Optional. Yeah, we can run here. Dude, man. What the hell? Hold on. Maybe we do too much. Let's just do 7. No, it does not work. It says non-hashable. But it works on this side. It's exactly the same code. Type error is not valid value for the expected return type. List not a valid value for the expected return type. Raise type error is now valid value for the expected return type. What the hell? Hold on. How about 1? Does this one work? Or 1? Okay, 1 works, 2 works. Well, just figure out what happened to 3. 3 doesn't work. Let's see. 3 pass in, right? So 3 divided by 2 is 1. So this one doesn't go. No, 3 minus 1 is 2. 2 down, so it doesn't go. So 2, right? We'll do this, do 1. Oh, I see. My bad. This should be root. Actually, roots. This is roots. Ah, that's why. Oh, we can just say for all 3 in this. That should be right. Come on. That should be right. Come on. Boy. Alright. Ugh. I forgot. I forgot it's a list. Then I don't even need to separate them, right? I can just do this. And I can do this. Yeah. None type is not iterable. Oh, it could be none. But could be 0. Ugh. If n is larger than 0. No. N is larger than 0. N could be 2. Hey. N divided by 2 could be... N divided by 2 could be... Oh, maybe I should do this. You know, yeah. It should be... Then I don't have to worry about this. Oh. No. No, I think the regular ones is all correct. I hope. No, I don't think so. 0, 0 is right. This is wrong. This is not right. Yeah, you know what? This shall be just none. Just don't, right, it doesn't really do anything. And we just have to check if n divided by 2 is if n divided by 2 is an even value. If it's an even value, then we just shouldn't do, right? If it's an even value, then we shouldn't even do. Yeah, n is an odd, right? We need to make sure n is odd. So n minus equal 1. Now n is even. N minus 1. Now n is even right now, right? And these I is odd. So this is odd. So we can guarantee these shall be right. So n is even. So n divided by 2, if it's even, then we shouldn't even continue because it's just impossible, right? So we say if this mod 2, right? So if this one is odd, then we do. How about here? That is still not right. Interesting. Oh, I think this one's already wrong. 0, 1, 2, 3, 4, 5, 6. Wait, hold on. 0, 1, no, 1, 2, 3, 4, 5, 6, 7. 7. 7. No, 7 is right. It's just ordered differently. Now which one? 20. 20 should be nothing. Yeah. 19. Okay, 19. Ugh. I don't know what goes wrong. It's hard to debug this thing. So anyway, 19 is not right, right? But why? 7, I think 5 is right. 7, how about 9, 11, 13? Try to see if one of them is right. Oh, yeah, we got it wrong. I think 9 is right. Hold on, you don't know. Just do one by one. 9. 9 is correct. 11. Eleven is wrong. 11 is wrong. Why? 11 coming in minus 1 is 10. So this can do 10, right? 10 divided by 2 is 5. So we can do 1, 3, 1, 3, 7. No, 1, 3, because it's 5. So 1, 3. Right, so it's 1. This will be 9. And whatever. So we fill up these. Then we come in down here. This is 5. So we do 5. And 5 have whatever it is, right? We have whatever it is. And then we do left and a right, left and a right, and left and right. Why is this not right? I don't understand. Expected. I mean, this didn't even tell me what expected is. I don't know. I mean, hold on. What do we have? We have 11, right? So I have this, I have 10. So we can do 1, 9. Of course, 9, 1. Or I can do 3, 7, right? And we can do 5 and 5. So this is a 1, this is a 9. And 9 is correct. However many 9s, different type of 9s we have, right? This will be 9. We get every single one of them, right? And we, on one side, we put, because this is, let's say 1. Okay, so only 1. So this is a bunch of them, right? So 1, put 1 of the 9, and then 1 here, 1 of this here, right? So blah, 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 done. And then we have 3, 7. 3 is only one type. 7 have whatever many. And now I have 5 and 5. Now 5, we have whatever different types of 5. So every time will be the same. The next one will be the same. The next one will be the same. How is this not right, man? And don't even know the actual solution. This didn't give me the actual solution. No, this one gives me the actual solution. Oh God. You're gonna decipher this? Dear me, man. You're kidding me. It is not gonna work. So you're trying to decipher the whole thing. I mean, they're not even the same. Not even in the same order. Okay, I have an all 0. Okay, do you have all 0 here? Yeah, you have all 0 here. I don't know. Especially all the other one is correct, right? If all the other one is correct, how come this one is wrong? Use the same idea, exactly the same idea. Could it be, you know, divided by 2, be 5. So what if I do 5? 5 minus 1 is 4. Okay, 4 minus 2 is 2. So it's only going to do 1. So 1, 3. 1, 3, 3, 1. Perfect. And then 4 divided by 2 is 2. And then we can now do 2. So I don't do it. Yeah, because we did 5. 5 is correct. That's very interesting because 1, 3, 5, 7, 9. I think all of them are correct. Unless one of them is not correct. All of them is correct, okay? All of them is correct. If all of them are correct, how come this thing is wrong? 11 is wrong. Because a common in 11, minus 1 is 10, okay? 10 divided by 2. 10 divided by 2 is 5, right? So 1 to 5. So we have 1 and 3, okay? So we do 1, and then we do 1, and then we do 9. And we know they're all correct. So we do 1, 9, 9, 1. All combinations, right? This one from 1, now we have all combinations on the right hand side, all combinations on the left hand side, and do this. Perfect, right? All of them done. And then 3. 3, 10 minus 3 is 7, so it's 3 and 7. So one side is 3, other side is 7. All done. Perfect. And then, once we're done, here, n minus 1. N is odd. N minus 1 is even. So this is divided by 2. We check if it's even or odd. And now it's 5. Right? Because 10 divided by 2 is equal to 5. So I do 5. And I get all of this. And I set the left and right. I don't understand. I have no clue. What did I do wrong? Did I get... I don't know, man. I have literally no clue. This is expected. But that's not gonna help. So, how are you gonna propose to deal with this? Well, for one thing, we can do let's try JSON. Prettify JSON. Okay. Format. It's not really helping. It's too much. Maybe I have duplicates. Maybe. Hold on. Do we have duplicates? I don't have duplicates. I don't have duplicates. You know what? It's stupid, but we probably have to do it this way. God, man, this is ridiculous. I hate this so much. Hold on. But we have to do it. So this is my answer, right? This is my answer. And all the null we have to return. Null become none. Okay? And we have the solution is this. Okay. All the null turn into none. Of course, I think it'll be easier if we do this one the same way. Just don't prettify it. Actually, I'm not even sure which one is the answer, which one is... Hold on, this is my output. Okay, this is the output. This is the solution. I think I'll just swap to be none. Actually, not sure. Can we? Yeah. Answer is much more. No. No. This is not the answer. This is my output. This is the answer. Yep. Yep. Okay. So we can just do the length first. Length output. Okay. Print length answer. Yep. I'm missing 2. Dear me, I'm missing 2. What am I missing? What am I missing? Exactly. Okay. Can we get what I am missing? We can turn this into a set. Yo, this is the weirdest debugging I've ever done. No. Yeah, that's stupid. Let me just copy and paste this whole thing and put it into a new file. We'll deal with this one later. Now I can just do all of them into a left parentheses and do all of this into a right parentheses. Alright? Then I can say for A in answer, if A not in output, print A. So these are the 2 we're missing. What are they? What the hell are they? Yeah, which 2 are we missing? We're missing 0. Okay. 1, 2, 3, 4. 0, 0. No, 0, 0, 0. And then 1, 2, 3, 4. So we have 1, 2, 3, 4. So that's 7. Right? So we have 1, 2, 3, 4, 5, 6, 7. Then I have 0, 0 on here. Okay? 0, 0 here. None, none. None, none. 0 and 0. So that 1, 2, 3, 4, 5. This is a 5. This is a 5. Okay. This is a 5 and a 5. I don't have that. You're saying I don't have that. That is bonkers. I must have... Oh. Oh, I think I know. When I'm doing this, I'm only doing the same... Because this has multiple. And they can mix and match. Oh my god. My god. So you're saying we should do this. Right? That's what you're saying. So if they're the same. That's what you're saying. We do a +1. Yeah. That's still not right, because now you have duplicates. Jesus. Jesus, man. Now we have duplicates. Now indeed we have duplicates. Because this will be 5, this will be 5, right? So 5 and 5. So I say this and this, perfect. This and this, perfect. This and this. And then facing the other side. Wait, hold on. How? How? Yeah, I think I have a lot more. Yeah, we can take 5. So we do 5 and then we do 5. Okay. So we do 5 and 5. 5 has 2, 3, 4, 5. 5 has 2 types, right? 5 has 2 types, either this or this. So I can say I'll do this shape and this shape, this shape and this shape, and this shape and this shape, this shape and this shape. That's perfectly fine. That's perfectly fine. It's probably the error with the other one. Hold on, let me think again. Let me think again. It's probably error with, hold on. Why would this not be right? That's not right. Expect. Right, expect is this or this. What I get, 1, 2, 3, 4, 5. I get that. And I get, what the hell is this? I got 1, 2, 3, 4, 5. I have duplicates, right? I have duplicates. Why do I have duplicates? If that's 5. 5 minus 1 is 4. 4 divided by 2 is 2, right? 2 plus 1 is 3. So I can get 1. And that's it. Yeah, 2 plus 1 is 3. You cannot get 3. So I just 1. So I get 1 and 3. I don't understand. And then you get 3. 3 down is 2. Right? 2, that would be 2. So it's still 1. So 1. 3 minus 1. 2 minus 1 is 1. Oh, the 1. 1, 1. It duplicated. That's true. That's true. At a 1, it duplicated. Because on the two sides is the same. I think the problem is when this is only for 1, and we basically R1 and R2 are the same. They're the same shape, right? Because this has only one possibility. This has only one possibility. So you shouldn't. What if we just do this? What do you think? Keep it simple. What do you think of doing this? Just to keep it simple. Right? I think you're complicating the things. Yeah, I'm seriously thinking you're complicating the things by running whatever scheme you are trying. Yeah. It could be so simple, right? Yeah, I think I was complicating the things. Just go through this, that's it. And then runtime wise, it's the same. Because you have to do it 2 times. The other you just go through. I don't know. I still think if we go to half and then we handle the half separately. Yes, I think it will work, right? But instead of we have to do, gosh, we have to do all 4. Right? We have to go through 2 times because I can have 3 and they can be the same. No. Doesn't seem to be right. Dear me. Why this idea is not working? I have no idea. I mean, it's so simple, right? You just this matching this, this matching this matching this, right? And the next round you go here, this matching this matching this matching this, and the last round this matching this. I seriously, I don't understand. Because I was trying to reduce the number of computation. And by doing so, I'm actually making it more complicated. Why is this one not right? No, it's not right. Oh, you're adding way too much. You're adding way too much. Nah, that's not right. Let's take a look at 5. This is a good case, just to see why this one's not working. Yeah, you're adding way too much. 3. Right? Let's try 3. Yeah, see? You're adding way too much. If it's 3, this one we don't do, so we do this. Right, that will be 1. So we do this is 1. Okay? So we get out 1. This get out is 1 as well. So this is 1. This has 1 as well. Why will I get this? Huh? Hold on, n equal to 3, right? So this pass. 3 minus 1, n equal to 2. Oh, that's why. Sorry. That should be right. All I want to do, yes. Yes, this is right. This is right. And the whole ideal is if I do it this way, it'll make it faster because I don't go through the whole thing. I'm not sure it's going to be faster though. I think it'll be probably the same. Maybe even slower. See? Because you add another layer, not another layer. So yeah, we're going to use this one. I think this one's pretty fast. It's good enough. All right. What is this? 173. 173, we can hit a 90%. Okay, so what we gonna do? This is a max OR. Dude, you just closed the thing. Stupid. I'm gonna copy this whole thing and paste it here. Uncomment it. Yeah, this one taking way too long. Thing is, it's not even that hard. I think I was just trying to, you know, do it smartly. Actually, I can just do it right here. Boom, that's it. Right, that's it. I think that's the solution. 4, 4, 4, boom. Yeah, that's it. I was overthinking it, that's for sure. Overthinking. $8.94. Yeah, I was way overthinking this. Just go through each subtree is count from 1 to n, right? All odd values, and that's it. Right, that's it. Don't think too much. What's the runtime on this? Ooh, good question. What's the runtime? Well, how many n, right? We call n, and we call n times is O(n) squared. Hold on. That's the total number of subtrees. I don't know. Like, is that 2 to the n? I guess it's probably 2 to the n. What's the runtime on it? 2 to the n. 2 to the n divided by 2. The maximum number of nodes that can be in the left subtree of all binary tree. The maximum number of nodes is n minus 2. Since one node is the root, and the one must be on the right, that's correct. The total number of possible full binary trees with n nodes calculated by considering all possible combinations of the number of nodes in the left and right subtree, such that the sum of the number of nodes. Oh. Yes. So that Tn is equal to the Catalan number, which is bounded by 2 to the n divided by 2. Oh. Okay, I don't know this. You think you can memorize this? You can remember this? No, no way. I'm not gonna remember this. for sure. All I can say is just don't overthink it. I think it's because of yesterday, right? I'm always thinking I can, solve the symmetry. I was looking for the symmetry. There's a symmetry here, so I think maybe if I do the symmetry, it can make it faster. The thing is, this one, the symmetry doesn't matter that much, right? And coming out, this like have to do another check, and then there's just too much things going on. It just really make it easier, right? Prone to error. This Catalan, what the hell? Whatever this is, I have no interest in learning. Like, if you're asking me, I would just say 2 to the n. It just feels 2 to the n to me, right? Because you're creating all possible trees, and it just feels 2 to the n. Yeah, I won't say it's difficult. It's just don't overthink it. All right. Anyway, so it took too long to deal with this. So this one, we failed yesterday because of TLE. So I thought about it, and here's my new idea. So this is not wrong, okay? This whole thing is not wrong. What is wrong, or what can be optimized, is we don't go through the entire numbers. Now, here's the thing. At the end, you're gonna OR everything, right? So it is always better to create a value, right? To create a value with just multiply by 2, all of them multiply by 2, right? If you can multiply by 2, just keep multiplying. Every time you multiply by 2, your binary value adding one more digit to the left. Adding one more digit to the left. Yeah, think about it, right? You have 1 something something. You multiply by 2. On the left hand side, just add another 1. Right? You multiply by 2, add another 1. So if you're handling this situation, right? So you have a value 1, 1, doesn't matter. If you, this one time 2, basically just add this one again, that you always creating a new position. And then this one, you always create a new position, right? So if I have a large value, I multiply by 2, I add, just however many times you multiply by 2, it add that many ones to the left. So if you have a smaller value, you multiply by 2, it does not change, right? For the final, it doesn't have any impact, right? It doesn't have any impact. Therefore, you need to choose the ones with like a lot of, basically you sort, when if you want to do it optimally, you sort this from large to small, okay? And for each one, you count how many digits, right? You count the digits. And once the digits dropped, you stop. Because the ones with smaller digits basically is useless. You want the ones with large digits. So now you have the ones with large digits. And then you do this. But instead of like say, okay, I multiply by 2 times, by 3 times, no. You just do k times, all right? Every single value you do k times, because when you do k times, you're always adding k number of digits to the binary value. If you don't do it, you like cutting short. I say I want to do I times on this value, and then k minus I times on that value. You do that, you create a shorter, you have fewer number of ones to the left. And then when you do OR, it doesn't really matter, right? It doesn't even matter. So you always want to create the maximum. So here is my new solution. I will first sort nums, reverse equal to true, okay? And then I will say max digit will equal to nums 0, binary this, and we do a line, right? Then we say to use nums to use equals this. Then for any nums, if len binary nums equal to max dig nums to use dot append n else break. So now I have nums to use, so n equal to nums to use. We can do all this. We can do all this. Fine. We'll do this. We'll do this. This is not right. So what we're gonna do is we don't do this. We don't even do the remaining. It's useless. We'll just do rest will equal to the maximum. Because I'm gonna. So I'm either two scenarios. Okay, two scenarios. So rest will equal to either I don't do myself or I do myself, right? Okay, so if I don't do myself, it's just gonna be dp index plus 1. Oh, I do have to, like, whether I've done it or not done it. So doubled mod has mod. It's going to be a Boolean value, right? So this will be has mod, whether it has mod or has not mod. And I'm going to do nums index or this, or we will left shift k, right? We'll just do k times, and this one will be has mod will be true. Okay, then we return this, and we'll do dp. Actually, why are you doing this is not necessary, right? And I don't think this one's necessary. I'm not doing this. Then we'll say dp0 and false. Okay, this is gonna work. It worked on the first one, doesn't work on the second one. That is very interesting. Oh, that's because I forgot. So it will be this, or dear God, I need to create. My goodness. Goodness me, I need to create the or of the remaining value of this. Remaining, I do have to if else num to use remaining or 0 rem or equal to n. Okay, so we'll return this or rem or. Okay, so this one's correct. Let's give this a shot. I have a giant test case here. It's not right. It's not right. Okay. Okay, how about I don't do any of this? Oh my God, you just change your mind. Maybe this analysis is not right. That's possible. Then we just do this. Is this right? Well, this is not even right. It's hold on. How? I thought it's the same thing. Has not modified. Otherwise maximum. I do not modify. I will hope some of this will be modified. Okay? Or I modify. And I'll find out the remaining. Because I have modified. There's nothing more you can modify. Why is this? Oh, I got 44. That's bonkers. Oh, because has mod. Okay, so if has mod, right? You know what? This might still be right, but hold on. This is not right. So if has modified, then I cannot modify myself, right? Then I just return nums index or has mod, right? If previous you already modified, then I cannot modify. So I just do me, do the rest. Otherwise, previous is not modified. I have two choices. How about this? This is correct, right? This is correct. So we're gonna submit this. How should I say it? Is that greedy? Like for each value, we must commit all the doubling, because splitting up the doubling on separate numbers is useless. Yeah, it's useless. Doubling, right? Doubling allows us to add one more digit to the left in the binary value, right? So to create a splitting up the doubling would always yield values with fewer binary digits. Thus, for each value, we have to double all the way down. This is O2N. O2N. Alright, try this. Oh my goodness. Wrong on so many levels, huh? What is this? 698. Hold on. Oh my god. So many wrongs happening here. Output 30. Expected 31. Interesting. Very interesting. I mean, seriously, what the hell? Expected 31. We have one doubling to do. One. Right? That will be one of the ones. Two. Someone shall do it. What? Is this not right? Start now modified. Right? False. So I can say I don't modify myself, I do this. Or I modify myself and I do this. And I try to find a maximum. What do you think? What was the problem? Okay, we start with 2, 0, 1, 2. Okay, I'm at 8. So if you are at 8 and you have modified, so you're modified, so 16, I agree. And now you're at 1. Yeah, I need to draw it out again. Hold on. So we have 6. What's 6? 1106. 9. 1001 is 9. 8. This is 8. So I say, you know, if you have this, then you'll double it. 16. If you're at this position, and you haven't done it yet. So it's 9, 8. Right? 9, 8. We either do 9 double. So I either 9 double, which is 1, 0, 0, 1, 0, and now 8 I cannot double, so 1, 0, 0, 0. So that will give a 1, 1, 0, 1, 0. So either this or this doesn't double, this one double. This will be 1, 1, 0, 0, 1. This should be larger. This is 16 plus 8, 24, 26. I think that's correct. 9, 8 is correct. So now we have 0. Okay, 0. So I think what I do is the maximum is here. So I do 1, 1, 0. Now we get 1, 1. Right, because I want to do, actually we can say 1, 1, 0, right? So I do 1, 1, 0, or, so either 1, 1, 0, either this, which give us 0, 0, 1, 0, 0, 1. This thing doesn't feel right, 1 plus 1 is 0, plus 1. No, you don't add. This is a 1, 1, 1, 1, 0. This is the answer I have, 30. But the answer shall be 0, 0, 1. Double this. 1, 1, 1, 1, 1. Oh. Oh. Are you telling me it's not DP? Because 9, 8 is 9, 8 or 8, 9. Like if you do 9, 8 or 8, 9, I'm pretty sure my algorithm is correct. Right? If you do 9, 8 or 8, 9, this should be correct. 9, 8 is not valid. Huh? What? Oh, dude. 1. Sorry. Forgot. Oh, no. What the fuck are you doing, man? Do this. Yes, right? 9, 8 is 26. But 6, 9, 8 is not 30. Because you're not supposed to get a maximum. That's the thing. You're not supposed to get maximum. Holy moly. Then what do I do? I mean, for one thing, we do find one value, right? We'll find one value to just double it to the end. Oh, you just try out every possible. Oh my god. Oh my god. You just. Okay, so. I know. Being stupid. Therefore, we simply choose each value, each big value, okay, double it to the end, and find the OR. Okay. Choose the largest among them. Okay, then we still have a question. How can we do it more efficiently? Right? How can we do it more efficiently? So I can OR everything first. Can I remove an OR? Can we remove an OR? I don't think you can. I don't think you can. Unless you can. Maybe. So what if we... Because otherwise it's going to take a long time still. So I need to count the number of ones at each position. Yes. I count the number of ones in each position. Okay? We count the number of ones at each position. Because if I OR everything, right? If I OR everything, I cannot remove one of the values. I can't. Because you don't know if that... Well, if you are a 0, then I guess, yeah, you can remove. But if you're a 1, how can you remove? If the OR of everything is a 1, and you have a 1, do you remove it? You don't know, right? You don't know. That's the thing, you don't know. So what do? You OR everything except for this one. Okay. You OR everything except for, let's say, the last one. You don't OR. You do it, and then you multiply everything. You OR them together, you get a value. Boom, good. Now you need to find this. Oh, yes, we can. Yes, we can. Yes, we can. Yes, we can. So basically, here's what we do, right? Basically, what we're gonna do is we OR all the way to the end. Do a prefix OR. Jeez. We do a prefix OR. So pre-OR equal to start from num0, okay? And then we say for I in range 1, 2, except for the last one. So len nums -1. We say pre-OR dot append pre-OR -1 or nums_i. Okay, done. So now we have a pre-OR, and we have a suffix OR. Shall equal to is 0 at the moment. Suffix OR at the moment is 0. Okay. Now, what we want to do is going from right to left. Okay, going from right to left. for j in range, dear me, for j in range from len nums -1 all the way down to the front, because every single one I want to multiply k times. Okay? All right. So for j in this position, and I have a pre-or, so I have a pre-or, so I need a res as well. This is the result. Okay? So now, for this position, I will first do nums j multiplied by 1 left shift k, right? This is that. So we will do a pre-or something, j -1. I think I need to start with 0. And I can do this. And this is not j -1 though, right? I shall be -1. I'll pop. Because the last one, or this thing, or suffix or, and the rest shall equal to maximum res and this. Okay? Once I'm done, pre-or dot pop, right? And suff or equal to nums j. Then we go to the previous value. The previous value, we will expand. We have this, and at the end, we return res. Is this right? Is this right? Are these right? They are right. Now we got this. Come on, now we got this. Let's get the giant test case. No, I don't have the giant test case anymore. Dude, I need a giant test case. You're just right. Yes. Oh, finally. Come on. Come on. Yes. Oh. So yeah, the implementation wise, we use a, I don't know what they're called. We use a prefix and a suffix all to keep. I don't even say. Well, how do I say it? We use a prefix and suffix all to find the all of the values ahead of and behind the current value of interest. Oh, and of course we can, skip some of the values, but I guess this one's good enough, right? It's good enough. Prefix suffix, one pass. Yes. Yeah, it's two pass. it's two pass. Oh wait, hold on. You can do O1 space. How'd you do O1 space? Wait. Backup or base and num. Base or num. base minus num or backup or, oh Jesus, what the hell is this? Base minus. I need more explanation on this. What is it? What's base? For every num, base and then base or equal to num. So every time base or and then backup is base and. You or a value and you and a value. No, you and a value first. If you and a value, back up. I don't know. I need more explanation on this. Do we have another person doing O1 space? It's the same dude. But I need more explanation. You can't just do this. What the hell? We only needed to keep track of 3 distinct states. None of the numbers has the current bit. Only one number has the current bit. That's true. And 2 or more has the current bit. This argument on O1 space. Do you understand? I kind of know what it's trying to do, right? None of the number has a current bit, but they need to show up, store the bits that show up a second time. Nah, I'm not gonna bother. The main idea is here. If we need to optimize, yeah, we'll optimize. But I still wonder though. It's kind of not my type, right? I really want to understand. And what does he mean by this? I'll think about it. But today, that's it. That's it for today. I need to end. It's already past 1 hour, 1.5 hours. All right, that'll be it. We solved the problem we got stuck yesterday, so that was good. I will see you guys tomorrow. Adios.